right. Well, so I thought I would start out with some slides that I cut from my slide deck in the interest of time. But since it just came up, I usually present on this topic of when selectivity becomes sensitivity. And I remember when I first saw something more like this graph on the left. And so to orient you, the blue line here is a precursor chromatogram. And then the colored lines are fragment ion chromatograms. And this is extracted from low resolution. This is like an LTQ. So that's why we don't have isotope peaks for the precursor. And then we just have these fragment peaks. So it's not as high resolution, but the same principle, I believe, applies. And it doesn't always even look this good. You know, this is another typical look at, this is high resolution data where you see so many more ions coming through here that, you know, I mean, it's 100-fold difference between, you know, the number of ions per second that are coming through on the MS1 and the number of ions per second that are coming through on the fragment ions. And when I started seeing things like this, when I implemented this in Skyline and I could see these side by side, I went into Mike's office and went, wow, we are going to get so much better quantification out of the MS1. I mean, it's going to be so much more precise because we have so many more ions, because he'd been telling me the more ions, the better. But then I started to see stuff like this where actually, you know, this is the same. This is, you know, this is a calibration curve experiment where we go 200 femtomole, 400 femtomole, and 20 femtomole. And by 20 femtomole, your signal to noise ratio here is almost swamped by noise, and the signal for the fragment ion still looks great. And so this is the same principle that that the original mass spectrometrists that I was talking to about SRM, and they were moving to SRM to do these experiments for CP-TAC, and what got me interested in targeted mass spec is that this phenomenon that we're actually, our quantitative precision is dependent on signal to noise. So decreasing noise increases signal to noise. And then Mike found the citation to what Sue Abitiello just presented in Boston when we were teaching about high precision assays. And so I felt that in DIA, we kind of, when we use MS1 label free and DIA, we kind of, you know, throw caution to the wind and let in a lot more noise than we're willing to deal with in a truly targeted high precision assay. But this is the phenomenon. You know, this is a publication where Rick Yost is the last author. He's the inventor of the triple quadrupole. It's from 1985. Here's the actual URL, and you'll get this slide. So you don't have to write it down. But this is the number of stages, and so I believe that actually a triple quadrupole has 2 stages. We're talking about MS2. But yeah, I was like, wow, you know, if we could get a non-quadrupole, then we could essentially get an infinite signal to noise. But we might have 1 ion and 0 signal, or 0 noise. So but whether you need, so that's selectivity, and it is really important to your quantitative precision, but how much you need it is dependent on your complexity. So again, if we're trying to measure something in cell lysate, that's a whole lot different from, you know, I have been working with pharma companies where they're actually creating biologics and they just want to measure a protein that they're generating in water. And it's like, okay, well, they should definitely just be quantifying with MS1 because they're going to get there's not going to be any noise. So you have to think about the complexity level when you think about how much selectivity you need. And then this is from the original SWATH paper. I usually show that, you know, there's this relationship on dynamic range where we know for sure that we get a larger dynamic range with SRM and SWATH, and then MS1 label free. We actually see a loss of linearity here, so I kind of consider maybe moving this line like that. And so anyway, so that's on selectivity. That's enough of that. I just wanted to bring that up since we were talking about it before. And then now I want to transition to what I'm going to be talking about. We're going to get hands-on with Skyline. get very visual and not run so many command lines. Actually, I wanted to ask, how many people for that last exercise wrote a batch file? How many people just typed into the command line? How many people actually wrote a file that they then ran? Nobody. Okay, so but when you're in the lab, do you keep a lab notebook or something? That's your batch file is your lab notebook. So when you're writing scripts, whether you're in the R, you might be in RStudio, which we haven't really dealt with yet. But anytime I'm in RStudio, you can type right into this console, but it's always better to type into a script so you can save it. And then so I did a script. So I did a batch file. This is my batch file for tutorial 1. And then I was able to Ben said, oh, it's exactly the same after a certain point. So this is my running search for tutorial 1, and I could see that, oh yeah, it's really just exactly the same after I do these comment searches. But I have a record, it's saved in my file, and now I can zip it up and put it somewhere and keep it. And I feel confident that if I want to go back and actually, if I wanted to tonight queue up a full run and process all 3 files, I could do that just by editing this batch file. And now I would have to rerun all this comment stuff. I mean, I have to not rerun the comment stuff, but I'd have to rerun this xinteract and the MyU and everything like that, and that would be lots easier because I have it in a batch file. And then yeah, you can see that the only thing that changes in terms of, so I've got a run search and I've got a build library, and the only thing that changes in the build library part is the cutoff, the false discovery rate cutoff. So just future note, like this is your programmer's lab notebook. If you're you'll benefit a lot if you actually get things into files and sort of never sit down and actually just type into a console. And so okay. All right, so yeah, I sort of got a blank check to talk about advanced DIA and Skyline, and I thought I would talk about what was forefront in my mind, because as I said, we've been working on implementing TRIC for a year, and I've got an intern who's going to be leaving, and we've been assessing, TRIC and trying to understand, trying to make sure that we can write a paper saying, yeah, it's as good in Skyline as it is in OpenSWATH, but and we've built a lot of ways of assessing this visually, and I think it's very informative how much information you can get if you have these sort of dynamic tools that allow you to, as I was talking to a friend who spent 10 years at Google, is now at MIT, and we were talking about being able to ask a question, get an answer, and go to the next question. And the longer it takes you to do that cycle, the harder it is to come to new understanding. But if you can continue that chain of question, answer, question, answer, question, answer, you can get places very quickly. And so, but anyway, so here we're going to be looking at the actual TRIC data. So this was mentioned this morning, and the goal, yeah. So So does everybody remember this TRIC? We haven't actually covered it yet, but it's the idea, or we haven't actually used it yet. I think you're going to use it tomorrow in the tutorial when you use OpenSWATH. But the idea is that, suppose you had, this is actually a completely missing peak, but suppose you had like a really little peak here that wasn't sort of good enough to make your M-profit cutoff, but then you could sort of align things and go, oh, you know what, because I can see it in all these other runs, I'm very confident that this is where it is. And so, this is something that I was really wanted in Skyline for a long time, and Dario, who I spoke about, who implemented M-profit in Skyline, and Hannes and I were talking about it a lot, and it looks like Hannes got it implemented in TRIC, and so now we've been following that up in the last year, working on it in Skyline, and we're going to actually look at the gold standard data, and we're going to think about like what does it take to validate that and to feel confident in that. And I hope that you'll also take a bit of ability away to look at your own results and validate them and make sure that just when you see, oh, I got 100,000 of these or I got 50,000 of these, that you can ask the next question of like, yeah, how can I be confident in that? So this is the TRIC methodology, and we've implemented this in Skyline. So there's this, you compute this guidance tree, and then you do a nonlinear alignment. And then you use this tree to transfer confidence from one run to another. That's basically it. Well, actually, so let's ask. So, I think sort of software, you should be as skeptical as your own data and in the lab. And so, like, what could go wrong here? What? Yeah, so it didn't pass our M-profit cutoff, and we say, well, what if we picked this thing over here? We said, like our retention time alignment somehow said, that's it, and actually we saw an example of retention time alignment going wrong when we looked at the chromatograms. I gave you some examples yesterday, that one where there were two peaks next to each other and one just got really big, and the algorithm chose that one. And so that would happen if those. In that case, we only had MS1, and MS1 signal can look very similar. So the dot product in MS1 signal is not harder to tease apart than in this case. You see there's a difference in the relative abundance of these fragment ions. So it's a little easier to tell that this is not this than if we had another isobaric peptide right next to it rising up. But the same principle applies. We have the danger of elevate, so we're going to transfer confidence from one run to another, and we have the danger that we'll elevate the wrong thing and get the wrong signal, and that will mess up, and we'll have a false positive, and it will mess up our quantification. All right, so then this is an ROC plot. Is everybody familiar? Everybody's familiar with ROC plots, right? So we have a false discovery rate here, and we have how many peaks we've identified correctly here, and naive is sort of M-profit the way you've done it so far, and then you can see that the curve gets better when we apply TRIC. So how do we know? Well, and then there's this experiment, which I'm really interested in, I'm going to go back and look at, but we're not going to focus on it today. So we have, this is 7,000 visually inspected chromatographic peaks groups. So it's 452 peptides over 16 runs. So that's kind of a hint. But how do we know what's true here? How are we? We're saying, we got some false positives. This is starting to go away. How do we know that we have false positives? What would you do if you were to do an experiment and you were like, okay, I want to make sure that the tool is picking the right peaks?
Positive control should be positive.
The what? Sorry.
I will take the non-peptide to make sure that I'm identifying the right thing.
Take the non-peptides? You mean the just decoys? Look at the decoys or something? Or? Well, so I'll explain how they got this ROC plot, right? Because in order to have an ROC plot, you have to have some prior knowledge of what is correct, right? And then you have to be able to say, you said it was this, but it's really this. So whoops, I'm going to score you an incorrect hit. So this is from the paper. 452 peptides were randomly selected. So they measured much more. They did a whole, like bacterium. Is it spiogenes? Is that a bacterium? Anybody? Yeah, spiogenes. What? Is it a bacterium? Do you know the spiogenes? Okay, never mind. So there's this Spiogenes experiment. As we'll see, it's going to be composed of thousands of peptides, as we're quite used to now. But they randomly chose 452, right? So that should give us some sense for how we performed on the others, right? We're going to do a random selection. That's a way of when you want to know what the entire U.S. thinks. You can't afford to go out and poll everybody. So what they do is they go out and poll 1,440 randomly selected individuals, and then they say, "Oh, now we have some idea of what the others think." And so that's this principle of randomly selecting some set out of your big set, and then they analyzed those over 16 runs. So they had done this experiment on 16 runs, and so they ended up with what this says in the paper is 7,232 chromatograms. So that's I guess peptides by runs. So this is 16 times 452, and then they used Skyline to extract the chromatograms for those targets. And then they identified by visual inspection. What does that mean? They went through it. They looked at everything, and they went, "Yep, I believe this," or "I don't believe that." And I guess we're gonna open that manual inspection file, and we're gonna look at it, and we're gonna try to imagine somebody, probably Hannes, sitting down, and what did he do when he went through and picked every peak? But that left him with a curated data set that he considered truth, and then you can do a comparison to what does the algorithm do, the automated algorithm do, versus what we believe truth is. And actually, we built a tool into Skyline to assess exactly that, so you can get the tool will generate this ROC plot for you, and we're going to do that, and then we're going to see how the further interactive UI that we built around that gives us the ability to ask and answer questions pretty quickly. So and then this is the other slide that was shown this morning. So what question do you have of this slide? So this is before TRIC, after TRIC. Visually the difference is really clear, and we're like, I like this one better because there's less variance, and it's got quantification matrix completeness. But what's behind this? What questions do you ask of this data when you look at it? Does anybody have a question? No questions? Like, you're reading this in a manuscript. How do you, like? Can you think of any way that we could get from here to here without doing anything very useful? Yeah, did it pick the right peaks? We could just artificially go up all the Q values and we could have an algorithm that went. And we know that this algorithm changes Q values. So we could just, if we had an algorithm, we have no idea what the correctness is here, but if we had an algorithm that just went through and sort of upped all the Q values, we could get a really nice consistent thing. So that's those are the kinds of questions you should be asking when you see plots like this, is like, so what other metrics do they have that confirm that they actually were getting right answers and not just a whole lot of new answers. So as I said, we've been implementing this ourselves, and I'm playing with this beautiful data set that it's a collected data set from 11 different sites that Ben and Christy Hunter I think organized, and then 11 different sites contributed data. It's all SWATH data, and it's got, you can see here, I'm processing about 125 samples at this point. Ben mentioned it, it's got 229 samples, and I call this the billion peaks, problem. This is a single document in Skyline, although I'm kind of starting to think, since I'm actually just doing reports by R, I could actually process each site separately and generate this same report, and that's probably a lot easier to do. I could do that on my desktop computer. To do this billion peaks case, I'm actually on a really big computer with a lot of memory. But so how I get to a billion is 1.5 million transitions for this document, 125 runs, and 10 peaks per transition. Oh, so this is the before, no trick. This is just the existing mProfit algorithm in Skyline running, and we can see telltale signs of issues like this. I mean, it almost starts to, seems like it's leveling off, but it's going up quite a lot. We'd actually kind of expect it to level off because we're getting fewer and fewer things. Like these are better runs than these, so we would really not expect them to be contributing a lot. So, but still, there's quite a lot of inflation. Then the blue line down here shows us how many peptides were actually detected in every run, and that's pretty cool. At like 6,000, this is across these. Each site contributed 20 runs collected over 5 days, and then this is like 6 different sites here. So kind of amazing that as many as 6,000 were detected by all sites. And then this red line is the number that were detected in at least half the runs, so that's pretty good too. I mean, it's nowhere near the 120,000 that Alexei just showed, but it's interestingly it's the same metrics. So there are extra metrics here to give us confidence in how well this data is turning out. And then the last one that I have is also this CV less than 20%, and this is a combination of things that appear. It's everything that's under this red line that also has less than 20%, and that's pretty big drop. But again, it's over 6 different sites and 5 days on each site. So this is then after this is early. So this is after our first implementation of TRIC, and it was like, whoa, we were excited because yeah, and I was sending email to Max going like, this is looking good, and why is it looking good? So why is this better than the last plot? The what? This levels off more, yeah. It's not as far from this, in half runs. So yeah, that's so again, what I'm doing all the time is going like, okay, if this really works, it should do this. And so that was one of the things I said, okay, if this really works, it should bring this down. And then what else do we see? Yeah, more matches. I mean, this goes up too. Actually, everything goes up. So this this comes down. That comes down, and so the yellow line comes down, which is what we want, and all the other lines go up. And so this was like, yes, we're paper in any moment. But there's one thing about this, like what I'm just like, this is a HeLa lysate. This is a human cell lysate, and I'm telling you that I'm using a very similar metric of confidence that Alexei's using, a 20% CV. I think I could guarantee that Alexei's not using a 20% CV over 125 runs collected in. So when people report their CVs, you want to ask, like, what's that CV over? Is it over 5 runs that you collected right in series? Or in this case, I think it's the CVs, the CV numbers are pretty good for 6 different sites collected over 5 days. But that's definitely a metric we're using. Okay, so what could... So if you were working out transfer of confidence, so this is a data set where what's the expectation? The expectation is that every peptide is in every sample, right? It's like The sample's not supposed to be changing at all. So how could that be a problem if I'm like, or what still could be a problem if I'm working on a transfer of confidence algorithm? What if I take it to a different kind of experiment where things are actually changing? Could there be problems that this wouldn't catch? What's a problem that this wouldn't catch? That if half my peptides are going away, what could an algorithm have still?
Some random matches and go in the wrong direction.
Well, yeah. I mean, I'm still dealing with this transfer of confidence. If I'm transferring of confidence into a place where there's nothing, the biggest problem is going off and finding something where there is nothing, right? And so in this case, I shouldn't really be exercising that much, right? Because everything's supposed to be constant. So that I was like riding home, going yeah. And then I went, oh no, we may just be like, yeah, this may not work in it. And then actually it turned out Max then fixed a bug. I said, oh, I fixed the bug, and everything went like that. And I went, what? And at first I was like, oh, that can't be the right fix to that bug. And then I realized that I'd had a bug in my R script, and so somehow they had combined to give us an overly rosy picture of what we had. But I still think it's good. This is what it's coming from. Whoa. So it's still an improvement. It's just not. And one thing you can see is the CVs go down. So actually, blinding you again. Why would you expect? Oh wow, what's your explanation for the CVs went up? So what's your explanation for, like, we started with 13.7 with less than 20% CV, and we went up to 14.4. And I was like, that's great. So why would that be? What's your explanation for that? Yeah.
Matches with a rather low intensity, so and the other ones are at a higher level, so the CV.
Yeah, well, so the CV would go up. So that's my explanation for why it goes down, is that it goes down because I'm drawing in stuff that's more I'm adding more variance. So that's my explanation for why it goes down. But my explanation for why it went up, and this is just the way the human mind works, we come up with plausible stories to explain things, is I was like, oh, it's going up because, well, this red line's going up, right? So that means that there are more things that appear in over half my runs, and wow, it's great that some of them also have low CVs. So the fact that this red line goes up means we have more candidates for low CVs, and then the fact that the black line went up was like, okay, some of those new candidates actually have low CVs. So that to me is we're not just adding junk, we're getting great new things that are measurable, that are low CV. And then when I came here, I was like, well, okay, I'm adding a bunch of stuff. It's unclear to me that I'm not sure I actually have. If I were to apply a 20% CV cutoff, I would have actually less things to work with in my next round. So if I were to say I'm only going to work with the things that have under 20% CV, what I just did doesn't get me anything in the next round. And then here also, this is another view where I don't think there is any bug. And this is just the number of runs that each peptide was. This is a histogram of the number of runs each peptide's identified in. So it's nice that we have a spike out here at about 7,000. What I showed you are almost close to 10,000. These are the ones that were identified everywhere, and that's great. But then there's this thing over here, which is things that were identified in one run, and those are probably all false discoveries, and we'd like that to just go away. But actually, the more runs we add, the bigger this grows. And you can actually see that it's starting to, there's actually a whole distribution out here. And these are probably accumulating false discoveries. So we don't like that. And when we applied TRIC, that got better. It didn't go away. We're still trying to, we're thinking maybe if we apply some of the peptide, the protein level false discovery rates and stuff, we might be able to get rid of that. But that's another thing we're looking at. So next question. Yeah, so I'm constantly saying to myself, fight confirmation bias. What else should I expect? And then I need to go to my actual results. What do you want to?
So I just have one comment to the slide you just showed before regarding the TRIC alignment, just for everyone to clarify. So basically what TRIC does is applying a similar thing as the global model that is also implemented in the jumbo pi profit. So the control that you can see, like if you go to the histogram of the frequency of observation, here, exactly. So when this bar is lower, this is actually something like providing this global FDR cutoff. So this is, but not only on the peak group level and not on the protein level necessarily, right? So this is actually like a on-top implementation, which is similar to what's done in the jumbo pi profit, but on the TRIC level. And the level that is kind of missing there is the protein level, right? So this is just
I'm not even sure it's as good as the peptide level. So we're playing with the whole peptide level, protein level, but we're playing with these. Anyway, so we are playing with the idea of global Q values. I mean, we work with, we're talking to the people here still at ETH, as well as Hannes Roast, who's still active and working from Stanford. And so they're all involved in this, and we're just assessing it inside Skyline. And so let's go back to actually using Skyline and looking at things. I would say keep going through the exercise of saying like, okay, well, if this really works, then I expect this, and try a new thing and fight confirmation bias. It's something that you get trained to do as a software developer. I actually think software development is a pretty good training for science, because you have to fight this will that this is very strong when you create a piece of software to go like, wow, it's great, it works, and then you have to start tearing it apart. And companies, I started working at Microsoft, and they actually hire testers because they're like, well, developers are too much in love with their own software. We got to hire people who are paid to break the software. And so I guess maybe that's what I have you for. But anyway, so so let's go ahead and get into Skyline. I did want to say that, like, that while that may be sort of the huge view is maybe a little bleak, this is the best run, and I think it was really quite nice. And these are all the plots that I'm using to assess these global things. And so this is this workflow that we've been going over. I just have a script that runs Skyline at the command line, takes a template, imports data, exports a report, and then runs an R script. And we actually ran this R script. Everybody who showed up for the morning session, we ran this R script, and we can look at it on the data in just a second. So this was, there was some normalization, but I mean, this is if I'm only doing 21 runs, this is looking pretty small, and this is looking pretty huge, and so it looks great, but that balance changes as we get more and more runs, and that's why we need the global Q values, and it's just a real nice visual indication that you can look at when you're looking at these data. And then this is CVs, and what I'm doing here is this is CVs only for things that are found in all 21 runs, and then I relax things to 19 runs. And so you can see that we're getting more and more things, but we're also shifting out to, there's more and more stuff out here. So as we bring in things, as we relax that, so you could certainly use, without adding any special Q value support, you could say, I'm only going to deal with, I'm going to do another round, and I'm only going to deal with things that appear in all 21 runs and have a lower than 20% cutoff, and you would get much more, precise quantification than your first round of this. But then you can start thinking about, well, what if I took 19? What if I took, and I go all the way down to about 10? And you can see that, we're getting more things, but we're also getting, more stuff out here. And then I have it's a little bit better if I do normalization. This is unnormalized versus normalized. And then I had a 2D plot, so you can get a sense of how that distribution shows up in 2D. So you can see that a lot of the poor CVs are at the lower intensities, and as we add things, we're adding things at the lower intensities, and stuff's happening out there. So this is all, this powerful method of run something and get some statistics. But I want to get back to, because you've been looking at a lot of statistics, I want to get you back to where you're looking at chromatograms. So let's. And questioning, whether these tools are picking things right. Okay, so there's my thing. So okay, so what we're going to be working in is so get your VM up, get Skyline up, and we are going to be working in this compare DIA folder. So this, I took some of the data that Hannes published. So he posted all of his data, and we started analyzing it and working on it. And then I created a set that I thought would be interesting to look at. But a lot of this is derived from Hannes's original data. So let's go through what we have here in DDA. Because I didn't want to add a whole lot of MZXML files, I have just bibliospec blib files. So that if you came in the morning on Tuesday, we built a bibliospec library. We pointed at some MZXML files, we pointed at a pepXML file and built a spectral library, a Skyline spectral library, and that's what this is. So I've just thrown out all the DDA files, and now I have a Skyline spectral library here. And yeah, I don't have any raw data in here. And then inside imported, you're going to see a set of files. Here again is that, I guess I have the library twice. So at the top, I have Hannes TRIC's Biogenes blib. That's the library. And then I have 2 IRT libs, which are IRTs. And then I have 4 different variants of the files. And these are sort of like pre-baked files. This is with the data imported. You can actually see .sky is the main Skyline document. .sky.view is what controls the window layout. And .skid is where all the extracted chromatograms live. And you can see that these are kind of big, some of them. 2 of them are kind of big. And that's, so if this is 16 runs, if I'd put all the WIF files on here, that would be huge. And I've managed to distill them down to about 4 gigabytes per variant that I did here. And we're going to come back to these because we're not actually going to, what we're going to do is going to design a document, and then we're going to just pretend we imported the data and work with these documents. Manual validation, that's the one we're going to open up in a second as soon as we finish review. This first one, Skyline results 500 peptides.sky that's just the raw file right off of the repository that Hannes published. And then this one I have corrected, and you're going to get, I think that there were some mistakes made in the manual integration, but you're going to get to decide whether you agree with me. And then open SWATH here, I have TSV, I have the libraries. These are the same kinds of libraries that you've been dealing with. These TSV files, and one is for, oh no, those aren't. Those are open SWATH results. So these are open swath results, and we're going to look at how we can look at those in Skyline in just a second. And then we have peak boundaries. So these are exported reports, which we're hopefully going to export ourselves from those files that we were just looking at, or at least once. And then finally, here's transition lists. And in transition lists, we have an IRT library, just like you've been working with, except that these are endogenous peptides. They did not inject the diagnosis standard or anything. So there's like 20 endogenous peptides, and that's kind of interesting to look at. And then this is the, you've been building these. These are the TSV files that are coming out of Spectras to TSV when you've been running that. And then in order for me to get them to work in Skyline, I had to fix the modifications. I had to do some sorting. And so I also put the originals here. So if you want to, actually, if you want to see my progression for, from the, I think this one's the original, and then I, changed the modifications, and I ended up with that, and we're going to hopefully use that in a second. And then these are 2 template files, and we're going to work in those. But before we do, I want to open up this manual validation file. So let's go to Skyline and go File, Open, Manual Validation. And we're going to not do the corrected one. Just open up the 500 peptides. So this is the one published with the paper. Wow. So kind of hard to see with all these legends here. Does everybody have all these legends showing up? Okay, if you do, you can get rid of them. So we actually have many copies of the same legend showing up here, and we can go right-click and turn off the legend. So now maybe we get a little bit better view. I'm also going to go ahead and take, how comfortable are people with rearranging the windows? Did you get some experience with that? Okay, so if you click on any title bar, right, you can drag it and it will turn into this floating blue rectangle. And then what I want you to do is put it over on the left side. And we do that by putting the mouse, the pointer, inside the rectangle, or that's on the right side, sorry, the other left side. On the right side here, and then release. And then you should get something that looks like that. And then I'm going to go ahead and grab the other one and drag it so it's floating, and I'm going to dock it below my peak areas by putting it by putting the mouse pointer in that lower rectangle. And so you should end up with something like that. Boy, that's going to be kind of hard to see, isn't it? Okay, so we're going to go View, Arrange Graphs, and we're going to say Grouped. And sure, we'll group by 4. And we want to make the sort order the document order. So is everybody arrange graphs grouped? View, arrange graphs, advance, or no, yeah. View, arrange graphs. And so then you want to set it like this. Actually, we'll go ahead and say distribute graphs among groups. So set it up like this. Is everybody there? Click OK. So now we have something where we could actually get some idea of what these are. And let's press F11 to zoom in to that's the chosen peak. So I tell people that the 2 most important keyboard shortcuts in Skyline are F11 and Shift F11. Get me zoomed in and zoomed out. And with this data, I've got almost the entire 140-minute gradient here. So So Hannes is, he's extracted everything, and then he's chosen some things out of them. All right. So now you can zoom in. So where do these predictions come from? Let's ask that question. Who can tell me where the so you can see it says predicted 50. Where does that come from? Maybe IRT? Well, so how do we find out? Does anybody know how to find out? Yeah. Nice. Yeah, so we go to settings, peptide settings, prediction, and we can see that there is this retention time predictor. And if we drop this and say edit current, it takes a second. We can see that it's actually it's a predictor based on SSR calc. SSR calc is the sequence-specific retention calculator, so it's just an algorithm. It's not a prior measurement. So IRTs are based on prior measurements, and this is one of those cases that I would give to Alexi as an example where prior knowledge is useful. But in this case, we're just using an algorithm. Somebody has written an algorithm, and it looks at the sequence and it predicts the retention time. It does a pretty good job, but we should expect less of it than we expect out of IRTs. So let's cancel out of here. And now let's right-click in retention times and look at the regression plot. So graph, regression, score to run. And so, yeah, here's that. If you didn't get that, you can also get to a lot of these things from view. So if you went to view, retention times, regression, score to run, you'd be there too. And here you can see, it looks like there's a number of peptides that were not actually measured in some runs, I guess. So let's replicates. So I'm currently set up for replicates all. I know some people were playing with changing what replicates get graphed. So this is some summary of all the replicates, and I might want to just look at single. Yeah.
Some of our plots look a lot different.
Okay. So you might have other calculators. So if you go to calculator, you might be like on the DIA course calculator or something like that.
Some people might have residuals on from yesterday.
Oh, residuals. Oh, okay. So anyway, yeah, I'll go to auto and it will pick the best one. And if you had residuals, you would have seen this. Plot residuals. Yeah. So that's the residuals, and you get this. These are the unmeasured things, and this is how close they are. And you can see that it's a lot more dispersed than what we were looking at before, right? This is like, we can drag a box out and just look at this main thing. And you can see that things are within 20 minutes or so, but they're definitely not, what? Oh, so actually we stopped before I switched to replicates single. So hopefully everybody has something. I mean, you can be looking at residuals or not if you want. I'm looking at residuals. I'm going to switch to single. And then now definitely we would like to see, not everything wildly move every time we change. You can see that things are moving a little bit. But yeah, we're expecting fairly consistent integration. How else will we check consistent integration over retention time? Wow, lots of ways. Actually, let's go ahead and look at this. We just went by this graph regression run-to-run. So this is a run-to-run comparison, and yeah, I expect my run-to-run comparison to be very linear. You might have to size it to get but you can see that I'm now looking at REPL2 RO1 RO2 and REPL2 RO3, and so I can change which runs I'm comparing, and hopefully this line here is things that weren't measured, so they've had their peaks removed. But what I would, be hoping to see is a very high linear correlation from run to run. And maybe, I can change the correlation method or the regression method to low S, and maybe then they get really nice. So that's what I would be expecting out of those. So let's go ahead and go view retention times replicate comparison is a great way to compare how consistently things are measured. I'll make this really tall because that can be nice. And then we can do multiple things at a time. We could do, I think we could do, well, it's not going to be everything, but with the top 100 peptides in here, if we just do Control A, does that work? No. Got to change Control A. And now we should be getting plots for everything. So there you go. Okay, so now let's bring up, so that's just a little bit of playing. I'm going to just select one thing again, and I'm going to double click on the title of my retention times plot to redock it. And so now let's go into this thing, where we can generate ROC plots and see how successful our peak scoring was, right? So go to Edit, Refine, Compare Scoring. And here's a little tool that we created, based on the work that Dario and Hannes were doing and how we were assessing success. And so if you read the original Open SWATH manuscript as well as the TRIC manuscript, this sort of curating a file and then comparing against that file and doing an ROC plot is used in both papers. So we'll go ahead and add a first comparison, and we're going to get it from a file. And this is going to be just Open SWATH. We're going to take the Open SWATH results and graph them against these peak picks. So again, somebody sat down and if you were doing this manually, like if you were going to manually curate a file without using an mProfit model or something, what more information might be useful to have? When we process it with mProfit, we get retention times predicted with SSR calc, or what do we predict our retention times with? Should have had that coffee break. Okay. Yeah, we predict it with IRTs, right? So it would be nice to actually have the IRT calculator in here. And if you look at this, we don't even have the, I'm going to cancel out of that for a second. We don't even have there are no libraries. There's no, we don't even know what the relative ion abundance is. So all of the things that, if we were in Skyline, we could look at a .p value. All the things that Ludovic told us we could use to assess peaks, several of them are missing here. And so if you imagine Hannes doing this, do you think he just went through these 140 minutes of chromatograms with just the SSR calc and no information about how well the peaks matched in relative abundance? How do you, can anybody imagine him picking the peaks? We're going to be looking at stuff like this. I guess let's see how close, why pick this one instead of this one? Or even, there's some coelution there, right? If you have no idea even whether or not this orange one's supposed to be the most intense, and this is just a sequence predicted retention time, I'm guessing that, like, I've looked at this a bunch, and I have to think that Hannes had a piece of paper next to him, and he was using some of the other information to help him figure out where this thing should be, because I don't think that a person manually can do this job that well. So okay, so let's now look at how this compares. So we're gonna go open SWATH, browse, and we're going to in compare DIA, we have open SWATH folder, and we have these two things. And what is the first one? It says no align all 1% mods files apex. So mods files apex I added. That's not the original. I had to make some modifications for it to work. So what is no align all 1% that you would expect? Does that have TRIC or not? No, because there's no align. And what is the 1% about? It's a 1% false discovery rate. So we don't have the complete results. We only have the things that we decided were below a 1% false discovery rate. But we can go ahead and add it and click OK. So open SWATH, add that file, click OK. So it's going to import peak boundaries. It starts off kind of slow. It speeds up, I hope. So it's got to import all these 7,000 peak boundaries. And then it says, imported file does not contain any peak boundaries for 3,288 transition group file pairs. Is that a message I should go, oh, yep, that's what I was expecting, or is it, whoa, I'm worried? Well, we had a 1% false discovery rate cutoff, so we know that we're not getting results for all of, so I say, don't worry about it. This is totally expected because we had the 1% false discovery rate cutoff. And then it says, well, you got 11,118 peptides in the peak boundaries file that were not recognized. Should I worry about that? Well, no, this is from this bigger search, right? So we've randomly selected a set of peptides, and that file that I just imported has information for lots of other peptides. Don't worry about it. And then finally it says, oh, but there's even 1,689 peptides which we don't recognize their charge state, basically. And it's like, yep, okay, some of these peptides had multiple charge states and we didn't include them all. So again, just okay. So 3 okays, and then you will have this ROC plot. And we can go focus on 1%, and that'll kind of snap it out. And we can see that, this is out to 5%. And this, after a bit of work, this actually matches really well what's stated in the manuscript. And, we have, but this is the actual observed false discovery rate. Is it a good or a bad thing that the Q value, when we reached an observed false discovery rate of 1%, the Q value says 0.0054? Is that good or bad? Good? Let's look at the QQ plot. So here's the QQ plot. And the QQ plot says, what a QQ plot, actually I think Lexi was the one who taught me about QQ plots. You want this line to be right on this line. And the reason it just goes horizontally over as soon as it hits this line is because of the 1% false discovery rate cutoff. So that's just, oops, we don't have any more data, and it goes across. But this is saying that our expected false positive rate at this point is higher than our observed false positive rate. Now, our observed false positive rate is higher than we expected. Yeah, there you go. So you want to, this is optimistic false discovery rates, and this is pessimistic. So if you're below, you're pessimistic. If you're above, you're optimistic. And so this means that I'm going to take more false discoveries than I desire, but not wildly by much. And this does sort of follow this line a little bit. So let's forgive him and move on. Okay, so now we're going to click on add. We're going to do open SWATH plus TRIC. So now we go to this, we're going to do the second one, which is result all targeted 1% local MST. So this is the trick, right? It's MST means the minimum spanning tree that TRIC uses. So, and then again, it says 10%, but it is a 1% false discovery rate, I think. Or maybe he did a 10% false discovery rate because the way of the way TRIC works. Okay, so once you get that, click OK, and you'll get a second. Well, you'll get some waiting for it to import. And again, we get these messages about missing things, and we already know to ignore them. So click through the 3 messages. Okay, so yeah, so it is 10%. See, we go all the way out here. Whoops. What happened? Are you kidding me? Oh, there it is. I don't know. My window disappeared. If yours did too, like click on Skyline and then click on it to get it back, and your window should come back. So yeah, so this is 10%. So you can see expected. So the first one cuts out at expected FDR of 1%, that's 10 to the minus 2, and the second one cuts out at 10 to the minus 1. So that means that he took a Q value of 0.1 for TRIC and a Q value of 0.01 for the normal one, and that's because TRIC at this point has this aspect of it becomes very pessimistic about Q values. So you can see now we're below the line, and when we cross at our expected false discovery rate of 1%, it's actually 0.5%. And this is like completely consistent with the manuscript. This is stated, and we're told it's a benefit of TRIC that, now we're underestimating our false discovery rate. And then this is how it looks on the ROC plot, and this would be fairly similar to what it doesn't go as far over as in the paper, the ROC plot I showed you from the paper, but it's very similar ROC plot. You can see that we're getting more correct, manually picked peaks. And then on this plot again, you can see that when this Q number is higher than 0.1, that means we're being pessimistic, and when it's lower than 0.1, that means we're being optimistic. Okay, so now we've looked at QQ plots. What else can we look at? Here's score details. I'm going to say that's maybe not so interesting right now. We'll come back to that one once we have some Skyline results. And then we could actually do a score comparison, and we could compare OpenSWATH to OpenSWATH TRIC, and we could start asking questions. What's a question you might want to ask out of a comparison between them? What?
So, which peptides could be identified using TRIC?
Yeah. It's like, okay, what? So it's, and I gave it to you yesterday. It was the question that I asked of Spectronaut compared with Skyline was, what's the best scoring peptide? What's the thing that TRIC is scoring so high that OpenSWATH alone is not scoring so high? So, but yeah, let's look at the ones that one got right and the other one got wrong. And we can do that by So peak match left, we want to look at false peak matches. So if you click on this header, you'll immediately get all the false peak matches. So you get, now we get all the false peak matches sorted to the top here. And then peak match right, we're going to want, is this going to work out? We're going to want to click twice so we get true peak matches. And now we have right up here at the top a set of things that OpenSWATH got wrong and TRIC got right. And we could go through and assess them. You know, let's... So let's look at this first one. So this is recently added to this UI. Everything's clickable, so we can click on these links. So the first one would be activate the right replicate. And I don't maybe have it. So that's the one. That's the replicate, but I'm probably not on the right peptide. And then I click on this peptide, and now I jump to the peptide, and we can see that there it is, and OpenSWATH, for some reason, we can actually look at the times that they chose, and we can say that OpenSWATH, for whatever reason, was choosing apex left. So it chose 94.8, and you know, where's 94.8? We're going to have to do a little scroll wheeling. Oh, it's this one. Is there something out at 94.8? Well, I guess it picked this, which I don't totally understand, but yeah, that's what it's indicating. And then with TRIC, it picked a better peak. Let's look at this next one. So click on this next sequence and click on the replicate to activate the replicate.
Is that the right field, Brendan, apex left? Because it's on true start peak, it says 91.23, right? So is that not?
True start peak?
On your grid, to the right of apex, there's other fields called...
Oh, yeah, true.
The right times, no?
Yeah, those are the times for the what's in the document.
Oh, I see.
Yeah, so we have the left apex and the right apex, and then we also have the true. So then we have the boundaries, right? And yeah, so what we're trying to say is, like, again, sort of stating what you believe is, okay, if this true false estimation is wrong, then everything on the left should be outside these two values, and everything on the right should be inside them. Right, and so we can go 99.79 is to the right of the end of this peak, so it's just to the right. And if you click on both the replicate and the peptide, you can see that it's this thing. It must have picked this. You know, I don't know why. But yeah, when you have jagged peaks like this, you know, sometimes we'll pick something that that isn't as right. Okay, last one. Click both of these. We're now on another. Oh, is this the same peptide? Yeah, this is the same peptide. So apparently this peptide was somewhat difficult, and in this one, again, we picked 90. The left OpenSWATH picked 94.56. So this thing out here, or no, it's even a little bit further right. I don't know. Yeah, that's some of those are hard to explain. But unfortunately, it's easier. It's usually easier to understand Skyline because we don't really know what chromatograms OpenSWATH was looking at. Okay. But anyway, so that's how we do that comparison. We're going to leave the comparison for the moment and start up a... Oh, actually, I want to do one. We haven't looked at this last tab, run comparison. So here, when we apply a Q-value cutoff, wow, I kind of remember this is more extreme. Is one tool better than the other? OpenSWATH with TRIC. Which one would you prefer? Can't really tell? Okay. Yeah, so to me, I have a memory of looking at this and feeling like, oh, these green ones are higher than the left ones, but now when I click the observed, if I use the observed FDR cutoff, then TRIC's actually higher. But before I did the observed, if you were just to go, okay, I'm going to take everything at a 1% false discovery rate, you'd say, hey, OpenSWATH's doing better, right? Higher numbers. But that's just an artifact of the fact that the Q values are calibrated differently. So you have to do something to figure out the Q values to know to say, oh, actually, TRIC's doing better because I can trust further out in Q values with TRIC than I can with the other one. So, okay, what else do people notice from this graph? Any other? Some other runs are missing, exactly. Yeah, in fact, all the RO1 runs are missing. So instead of having 16, and I've asked Hannes for all 16 and promised Max that I will come back with enough OpenSWATH knowledge to run all 16. But yeah, for some reason, we only have these 12. And I'm not quite sure why, but everything else sort of checks out, but worth noting that we don't have all 16. Okay, so now, let's see, how much do we do? Okay, eating through time. So let's go ahead and now, let's open up a new instance of Skyline. So that's our comparison instance, and we're going to go to Programs and start a new instance of Skyline. And we're going to open a file. And we're going to go to this compare DIA folder, and we're going to open up the blib version of this. So I've got an alib and a blib. That was my assay library, bibliospec library. So assay library are those TSVs that we've been generating, and a bibliospec library is what we can build inside Skyline. So we're going to go through using a bibliospec library first. So double click here to open it. And now go to, we're going to review the settings. First thing is we're going to be doing a quantitative experiment, so we turn on integrate all. And then now we're going to go through peptide settings. And the peptide settings should be mostly set up correctly. We're allowing 3 miscleavages, trypsin. We don't have a predictor yet. And we're filtering from 60 to 40. Some of these are pulled from that manual file, I think. But certainly, I actually started with, okay, let's start with the assay library one. Okay, leave that there, start up another instance of Skyline. Because, yeah, how that's configured sort of comes from how the assay library is configured. So, and then click open and open up the A-lib version. And so if you get an assay library from somebody, it doesn't always come into Skyline like completely pain-free. You may have to do some work to massage it. And in fact, in this case, I was not actually able to get absolutely every transition in Hannes's TSV to match up with in Skyline. So we'll see that. So, okay, settings, again, integrate all, right? And then peptide settings, and we have 3 miscleavages, no predictor, filter 6 to 40, library, we don't have a library. Doesn't matter, we're going to get one sort of auto-magically by importing the assay library. And then when we look at modifications, you're going to see all the modifications I had to come up with to support all of the transitions inside this assay library. And, definitely in correspondence with Ben, this is not what they would normally do now, but these were sort of loose. This is Spectrast, very loose parameters, and before they came up with really the best way to build these assay libraries. But so we're allowing oxidation M, we're allowing all the degradation modifications, pyroglue glycine to pyroglue, glue to pyroglue, and then we have ammonia loss on the C-terminal, or the N-terminal cysteine, ammonia loss, these are the normal ammonia loss and water loss, KN, QR, DEST. We kind of talked about those if you came to a morning session. And then it turned out that we had to come up with just a whole lot of losses to explain all the transitions. And in fact, we had to allow 2 neutral losses per fragment. So I think some of the neutral losses are highly unlikely. And I'm told that the assay libraries you've been generating are not this way. So I think we are okay here. So just okay. I don't know if we changed anything at all. And then go to transition settings. Monoisotopic. Filter. Here again, we have, okay, so the assay library that I got from Hannes, or that I got off the paper, has precursors 2 and 3. It allows ion charges 1, 2, and 3. And then we had to allow YB precursor and A ions to get everything. And then ion 2 through last ion, and we're allowed to exclude this. And then we're going to use 6 transitions. And we're going to have high resolution matching. And we're going to allow from the range from 200 to 2,000. And then finally, we've got the full scan settings, which are DIA with 18,000 resolving power. And this I think I just got from I mostly got from the manual. And then we have this, what I called SWATH legacy. If you edit current, you can see this 400 to 425, 1/2. 424 to 450, 1/2, and that's the published SWATH, no variable windows. It's the published out. So this is sort of old data, but yeah. So and then we're doing 5-minute windows, or 10-minute windows, 5 minutes on either side with from prediction. Again, okay, yes.
So here we have firstly chosen this use high selectivity extraction.
Yeah, so when because we've been using centroided data, so this is we're using a TOF mass analyzer. What I extracted from WIF files, and so I would tell you if you're going to process with Skyline and you have 5600 data, I've seen no benefit to centroiding, so I would just not worry about it. Just go ahead and import your WIF files. With some of the 6600 data, and Christy Hunter was really confused by this because she didn't really think this should be the case. But with the 6600, I saw centroiding working better. And so I tend to use centroiding with 6600 data and assume that it's worth it may still not be worth the effort because you're doubling your data size and stuff like that. So for SciX, it takes a fair amount of time to get centroiding, and you're going to want to convert. You're not going to want to just directly import centroided. So for SciX, I would say jury's out to whether or not you should just always import WIF files. 5600 data, I've never seen a benefit to importing centroided data other than that you can have a nice small file that you can give for a tutorial. And then for 6600 data, I've seen a benefit on one data set, and Christy Hunter's like, I want to send you a bunch of data because I'm not sure that that's real. So, okay, so hopefully I'll know more within a few months. So that's all good. Let's go back. Oh, we're going to, yeah, so now all we need to do, so cancel out of there. We didn't change anything. We're going to go File, Import, Transition List, which is how, I guess you've done this before, right? So again, yeah, you're doing, so we go to the transition lists, and you can see that we're going to import is this lib modified and then it's got mods, sorted, and TSV. And if you want to see all the changes that we had to do to this library to get it into Skyline, we have the originals, and you can diff them and look at the differences. And it took a bit of work. I think definitely the libraries you've been generating would come into Skyline much more easily. But it's not always the case that they're not always super compatible. Okay, so let's go and import it. Double click on it, and so it starts inspecting, and then it imports. And this is, a reasonably sized assay library, so it's not going to come in instantly, but it shouldn't take too long. Any questions while we're waiting? Okay. Well, let's go back. Let's go back to our blib file while we're waiting. So we're going to build this second one off the blib. And the reason I stopped is I was going across, and we're going to go ahead and we're not going to build edit. Yeah, we're just going to add it, right? Okay, so yeah, let's go add it. So in the library, we would, if we had pepxml, we would build it. But we don't have pepxml, we don't have mzxml, so we're just going to go edit list, add, and click browse. So now you're browsing. And in here, we can just go to this, so compare DIA, DDA folder, and here we have this, we see two blib files. One is redundant.blib and the other one's blib, and we never want to choose redundant.blib. Skyline will give us an error message if we do. We always want to choose the normal blib. So double click on that. And we'll call this Hannes Spiogenes, and click OK. So now, and then click OK again. Now you have this new library, and we can check it. And that's all we need to do there. If you go look at the modifications, wow, we only have, yeah. So this file, I didn't think Skyline would remove those other modifications. Oh, because we opened this file first. Yeah, so you can see there's no losses. We're not gonna allow for any losses with Skyline. We're just gonna let Skyline pick peaks out of the library with no extra loss ions, because those are not as trustworthy. I decided to keep the modifications just so that we'd have a similar count to what we had before. And then click OK. And now I think if we go to transition settings, those should all be the same. Yeah, they're all exactly the same. So we got two files that are really only differing by the library. What's the source of the library? Okay, so what? Oh yeah, I dropped. Yeah, okay. So yes, I just Y and B, because I don't want P's and I don't want all the and I certainly don't want to allow A ions. So click OK. Got that. Now we can go back to our other one, because I'm sure it's done. And it's showing us errors. Oh no. And I actually even this was so much work that getting down to this few errors with this file, that I added this little checkbox where I can actually see the line that Skyline's complaining about, because that can be useful sometimes. But we'll turn that off. And I'm just going to tell you that, yeah, none of these are a big deal. Some of these are like the precursor is outside the range covered by the DLA isolation scheme. A lot of them are that. So it turns out that they allowed some things that aren't really covered by the isolation scheme, and then there are just some transitions that we couldn't get to match. But there's going to be many thousands, tens, hundreds of thousands of transitions, and we only have 153 that we can't get into the file. So we're just going to go, great, okay. And then it says, hey, do you want to create an IRT library? And we'll say yes. And In this case, again, we're going to create it from a separate calculator transition list, and then browse for that transition list, and it's in transition list, and it's this step IRT small fixed 1 prot. And then we're going to have to choose an IRT database, and we'll put that. We haven't saved this file. We'll just put this in the root here. And what are we going to call this? So this is Hannes Spiogenes -alib. So these are the retention times we're getting from the alib. So Hannes Spiogenes -alib and save. And then click OK. It's given it a name here. It's similar to our file name. And it's adding the peptides, and it says, oh, we noticed that you have spectral library information too, and so go ahead and say create for that. And you can see this is probably bigger than the last one you did. Did it go really, the last time did it go really, yeah, you did like 18 proteins or something like that. So this is a whole proteome assay library for spiogenes. Nobody knows what spiogenes is? What? Spirococcus. Oh, Spiococcus. Yeah, okay. Spirococcus. Okay, so it's a virus, right? Is that what? A bacteria. Okay. This shows how much I know. Okay. Finishing up the import. We're getting there in just a second. Okay, so well that's taking a second, so let's go back to our blib file. So with our blib file, would people prefer to watch and wait, or no? Blib file. So with the blib file, now we've got this is all set up. What do we need to add? This is the same way that our morning file is now, right? We've got a library, we've got all the settings set up, and what do we need to add? Targets, transitions, right? And so you've frequently been building you built your spectral library with Spectrast, and you chose your transitions with Spectrast to TSV. Now we're going to choose them with Skyline. So we go File, Import, and what we really need now is the FASTA file. So File, Import, FASTA, and where's the FASTA? I really don't have the FASTA. Oh, that's really unfortunate. Is it in here somewhere? Well, I would import we have copies of this file, so I guess we're not going to get to import the FASTA file. We'll look at a process copy, but that's what we would do. We'd import a FASTA file. Skyline would pick all of our transitions, and then we'd be ready to import data. Oh, actually, we have to add decoys in both cases. So before we import data, we'll go back here. Wow, it's still finishing up. Really? Wonder if I can get that. Okay, well, while it's finishing up, So this is my work computer here in Seattle. And honest trick. Where is that? Really? I guess it must be on here. Has anybody's finished? It did. All right. Okay, good. So, Atlas. So this is everything I got off of Peptide Atlas. Spiogenes. DDA. Here it is. So that's the file, and now I'll just go. This is my ETH files, upload files, browse. That one. What is this? No, that's not it. Where is my FASTA file? Okay, I might have to just give up on this FASTA file idea. Oh yeah, that's not how I got them in here. Okay. Yeah, that's not how. Okay, we didn't import a FASTA file. There's another way. Wow, I don't know why I'm spent so long figuring that out. Okay. So let's get rid of my work computer. Go back here. Yay, mine came in too. So actually, in this case, I wanted to have exactly the same peptides as Hannes had, and just change the transitions. So if you go to compare DIA, transition lists, details, there's a peptides insert.csv. And so double click and open peptides insert.csv. Did everybody catch where that was? DIA course, compare DIA, transition lists, details. And then you can switch and you can see here are all the peptides and protein names. And so to get peptide, there's another way I can import a FASTA or a transition list. So now what I want to do is, well, let's do Control A to select everything in there, and then Control C to copy. And we go back to our blib, and what? Oh, where is this file? The file is in compare DIA transition list details. So if you get to the root of compare DIA, we have all these things: transition list details, peptide insert.csv, Control A, Control C, and you'll be caught up. And then, so here we're going to go to Edit, Insert Peptides, and Control V to paste. And that's a lot of peptides, so that'll take a second. Skyline, and Windows will say, hey, Skyline's not responding, but it will. Whoa. So if your window disappears, just click in the middle of Skyline and it'll come back. So now you can see all the peptides, but you can see also at the top I have this row which is not really a peptide, so you want to click on that and press delete to get rid of it, otherwise Skyline will complain. So get rid of that header row. And you have all the peptides with the protein names. These are the same set that's in, you know, I just opened up the transition list and took the things out of it. And then click insert. And would you like the Unimod modification for the, I guess we'll say okay. And then we got to wait a second again. Okay, so meanwhile, at the alib, all we have left to do, what do we have left to do before we import data? Well, I like to have the IRTs at the top, so let's go ahead and grab the IRTs and go select the IRTs and go Control X, and then go up to the top of the file and select at the top and Control V to put them at the top. And then we need, what do we need at the bottom? Decoys. So edit, refine, add decoy peptides, accept the defaults, which is just to double everything. You don't necessarily have to double everything, but that's what you get here. You know, that's the default. Everybody good? Okay? Click OK, and that usually is a pretty quick operation. We get a whole set of decoys at the bottom just in one big chunk. And then we can put the selection back at top. Control S. Oh, don't save it to the template. File, save as. And we're going to just delete the word template. This is going to be our Hannes TRIC alib file, and click save. So we leave our empty template, save the new location, and now this is ready to import data into, right? And so I'm going to close it because we're not going to import data into it because we don't have any data. We're just going to open up a new, and so then that brings us to this, the blib file version, which has the IRTs at the top. Let's open up the IRTs, have a look at them. Right, and some of them are telling that there's multiple charge states, but we can see the spectra in here. Actually, I'm going to reopen that file that I just got rid of. So coming back here, I'm going to open this alib, and we'll get to look at the difference in the spectra. These are coming from the same spectral library, but here are the spectra we get over here, and then in the blib file we actually have a truly measured spectrum, right? So that gives us some flexibility. If we want to change and say, oh, we want to do 8 transitions, we don't have to go back and find 5. You know, this is all, it's just part of the Skyline document. We could go and change it to do 8 transitions. Okay, so yeah, what do we need to do here? What's the last thing we need to do before this is ready to go? Oh, actually, there are more things we need to do. No, what do we need to do? What? I'm going to check my notes. I actually have notes here. And this is a PDF with notes about all this that I will send you. Yeah, wow, delete everything soon. Okay. All right, well, anyway. Okay, so there you go. We're going to add decoys, right? Edit, refine, add decoy peptides, okay. Now we got decoys at the bottom and all our peptides. One thing that you've done in the past, the libraries you've been building are 6 transitions and 6 transitions only, so you could consider edit, refine, advanced, and then you could say, I want a minimum of 6 transitions per precursor. And then that's going to get rid of some of my precursors. Not a whole lot, but now we have every so if you watch the status bar, I'm going to undo that, Control Z. You can see that, Control Y, I lost about 600 peptides because I don't have enough things to measure them. And if I were willing to allow all these losses and things like that, I might get more of those. But all right. So yeah, let's file save as that file. And we'll just delete template out of the name. Yeah.
We check the quality of a spectra for the IRT peptides.
Yeah.
If the quality of a spectra was looking better, we increase the number of transitions. It also means that all the other peptides coming from the streptococcus, they also must be having better transition, right? When we are increasing the number of transition to minimize the peptides.
Increasing. Let's talk about that.
There are 2 runs.
Yeah.
Which you compare.
By
the same way.
Yeah.
In one you have bad quality IRT
Yeah.
transitions.
Uh-huh.
Another you have better transition.
Yeah.
So it means that the complete run was affected in terms of detection in the machine, right? So where the IRT transitions are more in number, we expect the associated proteins also to have more transitions.
I'm really not. I'm not getting the point. So we're gonna have to take that one up later. Okay, so we've got this blib. So now, if we wanted to create files, so I'll actually show you the files that we're about to switch over to, and these are the pre-baked imported files, and you can see that I actually have 452 for assay library 452, and then I have 450 for the bibliospec library because actually bibliospec ends up with not enough transition to measure 2 of the peptides. But how would I get to those? How would I get to those files? I've got these 2 massive files. How would I get to where I only had these, I have a known set of things that I want. In fact, I'll give you a bit of a hint. If I go to transition list details, then here's the 452 precursors.txt. So we'll open that in Notepad. So again, back to transition list details. And here you can see that I've actually listed all of the peptides and actually their precursor charges as well. And these are my 452 precursors that are in that manually curated file. So how would I modify one of these documents to contain only those peptides? Would I just create a new document? Yeah, I would create a new document for sure. Well, no, I wouldn't. No, would I just create a new document? Yeah, I mean, I could more or less do that, but I'm going to show you another way. So yeah, I could do something with my pasted peptide list and my, but I've got all these transitions, and I would have to find the transitions, and So what we're going to do, we'll do it for just one of them. I think I'm going to do it for this one. So the first thing I'm going to do is actually select this top thing, top protein in the blib one. And then I will go shift down to the end. So shift and hold to the end to select everything and press delete. And that just gets rid of everything. Everybody should have saved this file already, so we don't care that we just deleted everything. And so that gives us just our IRTs. So we want to save that for a moment. And we'll say, and so file save as Hannes TRIC blib and just dash IRTs. Yeah, I deleted everything. Yeah, so all I've got is IRTs. Because I'm going to regenerate the decoys, right? I'm not going to keep. Actually, I've been thinking about that because we were talking about, well, what would happen if you kept a full set of decoys? So that's something I'm going to try later. But at this point, I'm just going to generate decoys based on my targets. But I just want to save these IRTs so that when I'm going to do something else to the other file that might get rid of the IRTs. So file. And we're going to reopen that blib file. And so there's the entire thing. And then we're going to go. Let's go delete the decoys again. If you're actually editing a file, you really don't want these decoys hanging around. So go delete them. And then go edit, refine. Accept peptides. And anybody who's feeling a little behind is going to be able to catch up when they open the next file. If you hello, okay. So now we go back to this list. Control A to copy, or Control A to select everything, Control C to copy, and then switch back to Skyline. Control V to paste. Now we have to say we want modified sequence and remove empty peptides, and click OK. And actually, no big deal if you haven't followed this. So this gets me my 450 peptides. Oh, it's only got 451. I'm not quite sure why. But then what I could then do is maybe rename one of them turns out to be an IRT peptide. I guess I'll just delete that, and then I would go file. Oh yeah, that's right. That's my 450. So right, I have a document for. My document for the blib file is missing too. It's 450. The alib should have all 452. And then I would just go file, import IRTs. Do I want to? Oops, cancel. No, I would go file, import document. And I would import that document of IRTs. And that would put those back at the top of my file. And now I have a complete file again. And I would go edit. And I'm moving fast, and I'm not expecting you to follow. Edit, add decoy peptides. And as you see, it's only going to add a smaller number of decoy peptides. And there you go. So this is now an importable document. This is, again, another document ready for import. So in this case, I created 4 of them. And so then I would now save this one as... -450, yeah, blib -450. Okay, so let's go and actually look at the imported data, train an mProfit model, and just at least get to where we're ready to export a report. So just now abandon this. We don't have any data import anyway. But do people feel like they learned a little bit more about how to? Oh, yeah.
So I suppose you do this importing the FASTA file with the targets because you are not looking for, you are only looking for those that are in the FASTA file.
Yeah, sometimes you would import a whole FASTA file. In this case, we're not importing a FASTA file. We're saying here are the peptides.
Those are the ones that I'm looking for. But you were also doing the FASTA file import with all the database, all the peptides that you got, proteins that you got from the.
I was looking for a FASTA file. I never found it. What we imported.
No, I know. But what I mean is, like, in that FASTA file, it's also only a set of only the ones that you want to find, or it's
maybe
all of them.
you know, in this case, it would have been the entire FASTA file.
Okay.
Because this is let's go back. So let's go ahead and file open.
So I got slightly lost there.
Okay, sorry. So right now we're down to 452 precursors.
Yeah, because you only want to find those. But what I mean is that if the FASTA file is also everything that you can find in UniProt of whatever.
Yeah, you can do that.
Those same proteins are the ones that are in the library, I suppose.
Yes. The peptides are in the library. We don't actually have any proteins stored in the library.
So could you also go to spectral libraries and go for the option to add all?
Yeah, you could do that too. That would not, if you did add all. So what she just suggested is we could, we could do it right at the top of the file here. Go to View Spectral Libraries. Here's our spectral library. You can see it's got 21,000 precursors in it, and we could just click Add All. If we had so there's a whole lot of stuff that I haven't taught you. One of them is you can create a background proteome. If you had a background proteome, you could actually associate proteins. But so this is a way to add everything in your library that's matchable. And I'd click Add All, and it would say, yeah, I just added this many, and I'm skipping the 485 that you have missing. And I go ahead and add all that, and that might take a second. But yeah, there. It put it all inside my protein that I had selected. But thankfully for undo, I can get rid of that again. But yeah, that's one way you could, and that's the way I did the Bruker test, because we weren't talking about proteins at all. So I was just like, how many peptides can I detect? So I just added everything. So that's one way to get in things. And if you were in settings and you actually set up in digestion something called a background proteome, then you could, at this point, if I check this and go add, it will say, hey, you don't have a background proteome. But anyway, so there's a bunch of different ways of getting things into Skyline. We haven't been able to cover all of them, but yeah, you now have documents, definitely documents built from just the PepXML. You don't need to go through Spectrast. You don't need to go through Spectrast to TSV. So let's go open the let's go open imported. So here we have some imported files. So let's open the big one first. Let's go ahead and do the assay library ones. So if I open up the one that's got, so Skyline, now querying on the assay library, it's going to take a little longer to open because it actually has 16 replicates imported into it. And you can pretend that you're waiting for the data to import. It's not as pretty. The progress indicator is not as pretty, but yeah, that's what you would otherwise be doing. And then here you have it. And I always like to select this IRT peptide. That's what this protein. That's why I put it up at the top now, so that I can look in this retention time plot. I get a pretty nice bird's eye view of how did I do picking them? Maybe this one's a little bit out of the where I expected it. This one maybe is not quite in the right place. So I may not have picked every single IRT peptide correctly. Another thing, well, when you look at the peak area plot, what do you expect of the peak area plot for your IRTs? Yeah, so, wow. And so I actually went into log scale, and then even when you're in log scale, so you can click on, these are all clickable. So you can click on, say, and you have to click twice to actually select the peptide. So then this one is in log scale, it's going up it's changing by 100. We can, so what order is this? The replicate order? It's a logical order, right? We talked about that. So if we want to right click and say order by acquired time, then now we can see that there is some sort of systematic fluctuation up and down and up and down and up and down of this last peptide, but its retention time is really stable. We're not trying to quantify by it. It definitely would not be a good thing to normalize to, but it seems to be relatively stable for retention time, so we're going to keep it. So okay, so now the next thing we would do is go, so this is, we just imported it. What do we want to do next? Just imported the data. Are we ready to export a report and do a test? We have to, something in the refine menu. Reintegrate, right? We have to build an mProfit model for this, and hopefully we're just going to make this workflow more streamlined. But yeah, okay, so let's go ahead and add a new model, and it will score the peak groups. While we're waiting for it to score the peak groups, when you look at the chromatograms for these peptides, is anybody see anything worthy of note? Do the peaks look really nice? Some of them. And the other ones, they have tailing, right? And so what about a peptide with tailing? Is not going to work I think is going to cause problems for generating IRTs from spectra, because a tailing peptide will continue to be identified, and maybe multiple times out here. And what we're really trying to predict is where's that apex. Okay, so now if you've got this up, do people have it up? Okay, so then click train model. Just as soon as it comes up, you can click that, and that will take a few seconds maybe too. And we will name this. So how do people like that model? What is good? What causes you concern? What do you see interesting? I'm going to name it Hannes TRIC Alib. Oh, it's Blib or Alib? Alib, yeah. Alib. So what do you think? Good, bad, ugly, indifferent? Well, I mean, it's again, it's proteome wide, so it's not what we've been used to seeing. There's actually a bimodal distribution of our targets. So, I think I think this is a deep library that they collected over many replicates, and it's not expected to be quite as good. But yeah, so actually the retention time difference looks pretty good. It's a relatively strong score, stronger than we've seen before. Library intensity dot product, we always expect to be pretty good. Intensity going negative is a little bit weird and surprising. And shape and coelution are good. And so, yeah, I mean, that's a fine model. So I guess we can take a quick look at the Q values, and the P values look pretty evenly distributed, right? We're looking for evenly distributed decoys. That's definitely one thing we want to see in our models. So that all looks okay. right? I have reasonable confidence in that as a model for this data. So click OK, and then click OK. Oh yeah. Click OK again. We're not gonna remove any peaks. And then Skyline's it's gotta calculate the peak group scores again. And I should have started with the smaller one because it would be so quick. But then it would look like everything, the other things you've been looking at. But so that is the more typical type of model for using a big library where you don't necessarily expect to detect everything. So yeah, how many peptides are we targeting? How many precursors are we targeting? 40,000. Yeah, so that's a lot. Let's quickly, I would love to show you the difference between the A lib and the B lib, and actually they're very similar, so I'm just going to skip that. But now once you've got it retrained, you can go ahead and save. Oh, and that's going to take time too. This is the problem with working with these big files. That's why a lot of the tutorials we've set up really small files for you. So who was here? Who was not here in the morning? Wow. Who's coming tomorrow morning? Okay. Since most people were here in the morning, you guys are really gluttons for punishment. Here's the import log. I got a fully imported. Did everybody get through an import and get to where they saw something that looked like this? Where I'm all DI Empire and stuff. Like this. So mine took 35 minutes. Does anybody else have a completed run where they know how long it took, or have you lost that? 35 minutes. Everybody took 35 minutes. So what I say is what? 33. Oh, you must be on a good machine. So I want to quickly go back to this multi-analysis.bat, and we're all going to run a full analysis tonight. So who's actually got? Yeah, you probably don't have multi-analysis.bat open. So let's go back to C, DIA course, data, scripts. Everybody got that? Okay, so then right-click and edit multi-analysis.bat in Notepad, and mine will just come up like that. So here's the one analysis that we ran. Now we're gonna go down here and select. Oops, that doesn't work. Does that work? Yeah. You can click on the numbers and select all the other rows. So we're gonna do analysis of all the different retention time windows and extractions. You Control X, and then paste that up at the top, and then you want to now paste go to end above the one that we've already done. So you should end up with something like that looks like this, where the one run that we've done is between go to end, and all the other ones are here. And we're gonna give Ben some great data on how well these VMs work. And yeah, Paul who set them up. And if this works out, we're gonna be a lot more confident in these VMs in the future. Okay, so and then Control Save to save that. And then right before you leave, so when you close up your thing, if you're getting ready to leave right now, do this, go ahead and do this. You just want to run this scripts multi-analysis.bat again. I'm not going to do it quite yet. Or should I do it? Because you guys are all coming in the morning. Do you want a break for the evening? Okay, let's break for the evening. We'll come back. We'll pick up with a little bit of a comparison. So yeah, so everybody get to this, because has everybody followed this? Or at least a few of you? Okay. You want me to go through it again? Help you? No? Okay, forget it. Anyway, so then you just run multi-analysis.bat, and it starts this latest one. And when we come back, all of us who did it should have, 10 more runs. And actually, you'll notice that if I go to DIA data, it started this is my new run here. So I'm getting a new folder for every time I do one of these trials. And inside the folder, you can see it's created a file already. And if you look at this folder, this has got a full set of files. This is a completed run. We've got a peak areas report, and we've got a SWATH benchmark report. So we followed this pattern of, set up a Skyline document, run the command line to import data, train a model, export a report, and then run some scripts on it. So we've actually exported 2 reports, peak areas and SWATH benchmark, and that's allowed us to make some plots. It's also allowed us to put some stuff in a log, which we'll look at later. But let's look at the plots. So first, at the top, we have peak area CVs plot. So let's double-click that. And this is, oh my gosh, what's going on? Oh, it's saying you are getting ready to run out of memory. Yeah, so I gotta close some of these Skyline windows down. So do you. And if you've saved everything, shouldn't be a problem. But yeah, the VM is not capable of running. It's an 8 gig VM. So what does it say? Your computer is low on memory. Share the files and close Skyline. Close program. No, cancel. Keep going. What did it do? Did it die? It thinks it's okay. All right, so I'm going to even close down Excel. I don't think it takes a whole lot of memory, but all right, so I've got this peak area CVs plot so here's my, oh, that's not that. So I've got one of these plots that shows me, the vast majority of my peptides, like 18,000 peptides, are all detected in every run, all 6 runs. People have that? Okay. And then I can see the CVs. So that's what that R script does. You've got it. And then last, we've also got this SWATH benchmark peptides. So this is a trial. This is exactly what we were doing for that paper, the Navarro paper. So today you ran your first trial of the Navarro paper, and these are the 3 organisms that are mixed, and this shows us the yeast in the orange, the human in the green, and the E. coli in the purple, and they're supposed to line up where they're basically lining up, but you can see that they're pretty spread out too. And then there's also, actually opens even quicker, is the protein version, which shows us the protein quantification, and that's a little tighter. So, and that's it. That's all you had to live through. Yeah. So actually, and if you have that log file open, that import.log, you can see that it's running. So this is the import.log, but we didn't lose our last import.log because that just gets. So here's our last import.log. It's just time-stamped in there. But anyway, we can come back in the morning, see what got run, and maybe do something, again, more visual. Go back to our comparisons. All right? Good night. Thank you for staying. See you in the morning.